in this set of Snap Circuits videos, we're looking at Project 431, the time delay 1 to 7 seconds, up to Project 465, the lazy cat. So Project 431, there it is in the book, and here it is on the board. And I've decided to add the fan to the motor there, kind of just to give a little extra resistance to the motor so our lamp lights more since they're connected in series. But here we've got, basically, as it says, a time delay circuit. So our relay is controlling two different outputs. We've got our red LED connected to the normally open side of the relay, and then when it's closed, it will engage the 6-volt lamp in our motor. And of course, we're running 6 volts here. We don't have our 3-volt pack because we're using our battery eliminator. Obviously, everything is turned on and off via the slide switch. And then for the time delay control of the relay, on this side we have our press switch. And what that does is it charges up our 470 microfarad capacitor down here. And when that's charged up, once we release that, it's going to discharge through our NPN transistor through the base of it. And the delay is controlled via our variable resistor. So how much resistance we have here determines how long the delay lasts until the capacitor is completely discharged, in which case our relay opens back up again. And we got a 100 ohm resistor and our 10,000 ohm resistor helping with that, and then we've got a diode coming off of our emitter on the NPN there just to eliminate any reverse bias on it. So when we turn the switch on, our red LED comes on as you would expect it to, because again the relay is open right now, so it's only going through this contact here. Another little thing I should mention is that in the book it shows a 2 snap across here. It's a little redundant because the relay already has these 2 points connected. I figured I'd point that out as well. So if we set our variable resistor all the way to the left here, we have the lowest time delay, which is only about a second or two. So press the press switch. Our relay closes, it turns on our 6-volt lamp and motor, and when I release it, the circuit turns off after about 2 seconds because there's a lot of discharge happening through here on this side because we're at the lowest resistance. Now if we go to the opposite side, now we've got the most resistance. So if I press it again, now the circuit will stay on for several seconds because with more resistance it takes longer for our capacitor to discharge through the base of our NPN transistor there before it runs out and then causes our relay to open back up. And of course we can vary this by however we set the variable resistor. So by changing the variable resistor around, we can adjust how long that delay is. So that's how project number 431 works. Now project 432 is time delay, and all we're doing with that is we're simply going to change our capacitor here, our 470 microfarad, for a smaller one, which in this case is the 100 microfarad. And when we put that into the circuit, as you would expect, since we've got less capacitance here, our time delay on the circuit will be a lot shorter. So we'll put the most resistance on there for the longest delay, charge it up, and the circuit only lasts about 3 seconds or so as opposed to several seconds with our 470 microfarad here. Now if we put it all the way to the lowest resistance, well, the circuit pretty much only lasts less than a second. See, it hardly stays on long enough. So with using less capacitance, we have much less delay on the setup there. So that is how project 432 works. Now we're going to move on to project 433, which is the manual 7-second timer. So here we have project 433, the manual 7-second timer 2. There it is in the book, and here it is on the board. Now what we've done here is we've taken our NPN transistor and put our whistle chip with it, and basically took our motor out, put our lamp across as the output. But what we've done is we've created a link across our relay here between the switching point for the contactor and also the output switch. And as you know, when that happens, the relay tends to turn on and off really, really fast, creating a buzzing noise. And we're using the buzzing noise created by the turning on and off rapidly of the solenoid there to output to our whistle chip to create a tone. And it's supposed to last about 7 seconds, as it says, because our 470 microfarad capacitor down here is again discharging through the base of our NPN transistor after we charge it up. So with the circuit turned on, nothing's going to happen, obviously, but when we press the press switch, we'll charge this up, and we'll turn our NPN transistor on, which of course is going to activate our relay really fast and produce that noise. And then you see it dies out after a few seconds, so when we begin to press the press switch, charges our cap up, turns on our NPN transistor, and by having that connection across the contactor and the switch point, and again we're turning the relay on and off really quick, and then we're getting more of its output by putting it through the whistle chip. So that is how Project 433 works, and now we're going to move on to Project 434, which is the 15-second alarm. There are Project 434, the 15-second alarm. And there it is in the book, and here it is on the board. And so we're still using our relay and NPN transistor to turn our relay on and off, but this time the output of our relay is switching on and off our alarm IC, and the alarm IC's output goes to our speaker so that, of course, we can hear the output from the alarm, still using our 470 microfarad capacitor as the delay for how long the NPN transistor stays turned on, and we've got our 10,000 ohm resistor for how much current discharges through the base of our NPN transistor from our capacitor. So ready to turn the circuit on. Obviously when the capacitor is discharged, nothing's going to happen, but when we charge it up and energize our relay, it turns on our alarm IC, which we hear the siren from our speaker, and it does that for several seconds until the capacitor completely discharges. And now that the capacitor is completely discharged, the relay turns off and of course cuts the power to our alarm IC. We can of course repeat this process. So that is how project number 434 works. Now we're going to move on to project 435 through 443, which is another thing with our 7-segment LED display. So here we are with project number 435 through 443. So we're starting with the first one, which has the flashing 1 and 2. There's how our circuit looks, and here it is on the board. So we've kind of seen this circuit before with the alarm IC, but we've got the whistle chip for the audio output, but it's still driving the segments of our 7-segment LED display to produce different symbols and outputs. So we're kind of doing numbers and some more letters this time. So the first thing it has us do is start with the number 1, which just has us connecting points C and B, so we're just lighting these two rightmost segments up. So when we turn the circuit on, it flashes the number 1 on our 7-segment display as the alarm IC turns on and off, and we can hear the alarm IC's output through our whistle chip every time it pulses on and off as well. So that's it for doing number 1. So now we're going to connect points A and B, which we've already got, G here, E and D. So I'll just move this one to here, and we turn the circuit on this time. Now we get the number 2 flashing. So that's project 435. So project 436 is the flashing 3 and 4. So we're going to connect A, B, G, C, and D to the circuit. So we're going to move that one over, and we turn it on, we get the flashing number 3. And now we're going to connect C, B, G, and F. So we don't need A. We have B there. And we have C. And we have G. And we're going to need F. So if I put this one here, turn the circuit on, and now we get flashing number 4 on our 7-segment display. So that's project number 436. Now project 437 is the flashing 5 and 6. So for 5, we're going to connect A, F, G, C, and D. So we're going to connect A there. Let's see. F is still going to be connected. G we've got connected. C we've got connected. And D. So I'm going to pull that off of there and move it to D. We turn the circuit on and we get the flashing number 5. Now to do the number 6, we're going to connect A, C, D, E, F, G. So A is connected, C is connected, and C, D is connected. E needs to be connected up. We got F there, and we got G. So we turn the circuit on, we get flashing number 6 now. So that's project 437. Project 438 is the flashing 7 and 8. So we're going to connect A, B, and C for number 7. So B, C, and A, so we're just going to disconnect the rest of these. We turn the circuit on, and we get a flashing number 7. So to make the number 8 flash, we're going to connect points A, B, C, D, E, F, and G. So we get A, B, C, D, and E, and F, and G. And now I got a flashing number 8. So that's project 438. Now project 439, we're going to have the number 9 and the number 0 flashing. So for 9, we're going to connect A, B, C, D, F, and G. So we're just going to take E off of here. And we turn the circuit on, we get a flashing number 9. And for the number 0, we're going to connect points A, B, C, D, E, and F, but no G. So put this back here, take G out. And now we got the flashing number 0. So that's project 439. Now project 440. We're going to be flashing a lowercase b and a lowercase c. So for B, we're going to connect points C, D, E, F, and G. So we're going to take A and B out of the circuit. We're going to put G on there, turn it on, and we get a flashing lowercase b. Alright, now to flash the lowercase c, we're just going to connect points A, F, and G. So we're going to put A back on here. I got F there, G there, so take C, E, and D away. Turn the circuit on. And now we got a flashing lowercase c. So that's project 440. So project 441, we're going to have a flashing lowercase d and flashing lowercase e. So for D, we're going to connect points B, C, D, E, and G. So we're going to take A over, got B, C, get it on there, D, E, and G. So we don't need F. So we turn our circuit on. If we get a flashing lowercase d now. And now for the lowercase e, we're going to connect points A, B, D, E, F, and G. So A there, B is there. We don't need C, so we'll take that away. D, E, and F. And then we got G there. We turn the circuit on. And we're flashing a lowercase e. So that's project 441. So project 442, we're going to flash a lowercase h and a lowercase o. So for h, we're going to connect points C, E, F, and G. So don't need A, B, but can hook up C there. Don't need D. We get E and F and G. So we turn our circuit on. And we get a lowercase h flashing. And for the lowercase o, we're going to connect points C, D, E, and G. So we have C connected there. We need to connect D, E, and G. Don't need F. Disconnect that, turn it on. And now we got a lowercase flashing O. So that's project 442. Now project 443, we're going to flash a capital A and a capital J. So for the capital A, we're going to connect points A, B, C, E, F, and G. So A there, B here, we got C connected, we don't need F, so we don't have that, we have E, let's see, we do need F, and G, don't need D, take that away, and now we have a flashing uppercase A. Now for the letter J, we're just going to connect points B, C, and D. So we don't need A, C, and D. I'll just move it here. Remove E, F, G. Turn the circuit on. And now we got a capital J. So that's it for project number 443. So now we're going to move on to project 444, which is the alarm timer. So here we are with project number 444, the alarm timer. There it is in the book, and here it is on the board. And we're going back to using 3 volts. And this is kind of an interesting circuit in how it operates. We've got our alarm IC, which is outputting to our speaker, so we're obviously going to be hearing some sound. We have our 6-volt lamp here connected on the collector part of our NPN transistor along with the alarm IC, which is also feeding our 100 ohm resistor and our D1 red LED. Now coming up to here, we have our PNP transistor, and our NPN's base is connected through another resistor to the collector of the PNP. So the PNP transistor in this case is being used to turn on the NPN transistor because it connects the base of our NPN to positive voltage through the PNP transistor. And the PNP transistor's base is triggered through the resistor 5 here, a 100,000 ohm resistor to ground. So that's what's turning the PNP transistor on. Then over here we have a press switch, and this is going to be used to charge up our 470 microfarad capacitor, which, once it's charged up, will discharge through our R5 100 ohm resistor because it's in parallel with it. Now what's going to happen is, when we turn the circuit on, you see that our 6-volt lamp lights up, but there's no sound or anything, in the D1 red LED is not lit up. Right now, both the PNP and NPN transistors are in their on state. So as I said, the PNP transistor is being triggered via the ground connection through its 100,000 ohm resistor, which connects the base of our NPN through a resistor to positive, which of course is turning that NPN transistor on, allowing current to go through our lamp and then to ground. Now when we turn on our press switch here, when we press that, we charge up this 470 microfarad capacitor, and because positive voltage is here, that's going to turn off our PNP transistor, which in turn is going to disconnect the power from the base of our NPN transistor, turning that one off as well. And then what's going to happen is current's going to go through our 6-volt lamp, not enough to light it, but it's going to go into our alarm IC, and then through our 100 ohm resistor and red LED, turning those on. And then after the capacitor is fully discharged, the two transistors will come back on again, turning off the alarm IC and turning our 6-volt lamp back on. So when we press the press switch, the light goes out, our red LED comes on, and we get sound from the speaker. And as you see, once the 470 microfarad capacitor completely discharges, the transistors come back on, turning on our 6-volt lamp and cutting off power to our alarm IC in red LED. So that's how project number 444 works. Now project 445 is alarm timer 2, and what we're doing there is we're basically going to reconfigure the circuit a little bit so that in the case of that we're going to change around some of our resistors and capacitors. So let's see. We want to have resistor 5 and capacitor 3. So we'll take this one out and put capacitor 3 here instead. And I'm noting in the book here how they want us to rebuild this circuit a little bit, but from what I see, I don't really see the change. All they're really doing is changing where the point is on the alarm IC for a different sound output. Don't really care. But anyway, so we put the 10 microfarad capacitor there. So what do you think is going to happen this time? It's much less capacitance than our 470 microfarad, so it's going to only last a short duration. See. So a 10 microfarad capacitor, it lasts maybe a second, possibly less. So it doesn't last that long with such a small amount of capacitance. So now it wants us to use resistor 4 and capacitor 4. So for that, we'll take this off once again. And we'll use our 100 microfarad capacitor. And it wants us to use resistor 4, so that's 10,000 ohms. So we've increased the capacitance, but we've lowered the resistance. So what do you think is going to happen in the case of that? 100 microfarads, 10,000 ohms of resistance. As you see, it lasts about the same as the 10 microfarad capacitor with the 100,000 ohm resistor, because we've scaled up the capacitor by 10, but we've scaled back the resistor by 10 as well. So in essence, C5 and, well, not C5, C3 and R5 and C4 and R4 are equivalent, because Again, they changed by a factor of 10 relative to each other. So pretty much they both react the same way. And then the last is resistor 4 and capacitor 5. So for that, we'll take this capacitor back off, and now we're going to put capacitor 5 back on. So we're back up to 470 microfarads of capacitance, but we only have 10,000 ohms of resistance. So obviously more current is being drained out of the capacitor, thus the delay is going to be shorter, so it's not going to last as long. Turn the circuit back on, charge the cap, and so it only lasts about 2 to 3 seconds now versus several seconds when it had a 100,000 ohm resistor, because now there's 10 times more current there being discharged to the 470 microfarad capacitor. So that's how project number 445 works, and then project 446 is alarm timer 3. And what do they want us doing with this one? They basically just want us to change the sound output from the alarm IC. Let's see how I can do this. Do it this way. Do that. No, wait. Do it this way. There, that's pretty much got it how they want it. And we're using R5, C3, R4 and C4, and R4 and C5. So basically the things we have again. So we've already got R4 and C5 there, so we'll start with that. So basically it's going to behave the same way as the previous circuits, it's just that we got a different sound effect from our alarm IC because we're connecting it at different points. So again with R4 and C5, last maybe 2 to 3 seconds. So let's do R4 and C4. So let's put our 100 microfarad cap on there. Turn it on. And as before, this will only last about a second or less because of the difference in capacitance there. So again, it's only lasting about a second or so. And then last is R5 and C3. So we take that off, take this off, put R5 there, put C3 here, stick it back on, and it does it. And again, just like R4 and C4 before, you know, they last about the same amount of time because basically R4 and C4 and R5 and C3 are equivalent to each other in how they work relative to their capacitance and resistance. So that's pretty much it for project 446. So now we're going to move on to project 447, the bird sounds. So here we're at project 447, the bird sounds. And there it is in the book, and here it is on the board. And so we've got ourselves another oscillation circuit with our NPN transistor coupled with our 3 different capacitors and 3 different resistors, and then outputting that to our transformer, which is stepping the output down and playing out of our speaker. So when we turn this circuit on, it will charge up our 100 microfarad capacitor here, which will then start the oscillation process, and we'll hear that from our speaker. In the case of this circuit, it's supposed to make it sound like bird sounds. So I turn the switch on. After about 2 seconds or so, the capacitor charges enough, and now you get what sounds like a chirping sound coming out of the speaker. So that's essentially how Project 447 works. As it charges up, it makes the circuit oscillate back and forth on and off, and with that we get a frequency, and then we get that out of our speaker as it's passed through our transformer there, because it's an alternating signal. So with 448, we're just going to modify the project and change our capacitor around there. So first we're going to change it to a 10 microfarad capacitor, so we're going to lower the capacitance down. So when we do that, 10 microfarad is this one. So generally what happens with these oscillating circuits is when we lower the capacitance, it actually makes the circuit oscillate faster. And then when we increase capacitance, it oscillates slower. So when we put this 10 microfarad capacitor on there, the circuit should oscillate a bit faster. I need a moment. So the 10 microfarad capacitor is installed now. So when we turn on the circuit, it should take a lot less time to begin oscillating, and it should be oscillating faster. And it does. Now it's a really rapid chirp coming out of the speaker, and again, it didn't take very long to start because there's less capacitance there. So that's how the circuit behaves with the 10 microfarad capacitor. Now what we're going to do is change it out for the 470 microfarads, so we're going to increase our capacitance quite a bit instead. So put the 470 there, move that out of the way, get it back in there, get this reinstalled. And so, with the 470 microfarad capacitor, there should be two things that happen. One, the circuit takes more time to charge up the capacitor, so there's going to be a delay before we start hearing anything. Number two, it should make the circuit oscillate slower, so we should get like a chirp, 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 would be my guess, something about that rate, based on what we had with the 100 microfarad and the 10 microfarad. So let's turn the circuit on. Again, we got a delay. Waiting for it. And now we got the circuit oscillating. As we said, it's a much slower chirp. So that is Project 448. So with Project 449, we're going to put the 100 microfarad capacitor back. And this time we're going to make use of our whistle chip to alter how the circuit operates, and also change the sound output as well. So put the 100 microfarad back on our base grid. Put that in there. Put that in there. So circuit should be back to the way it was before, and it is. But now what we're going to do is we're going to apply our whistle chip. And of course the way the whistle chip is constructed is not only does it emanate a sound, but it's also constructed in such a way that it adds a little bit of capacitance to the circuit where you put it. So when you install it, it adds capacitance. So what we're going to do is we're going to basically connect it across the NPN transistor. So let me do that. So now the whistle chip is placed across the NPN transistor there, and now you hear sound emanating from the whistle chip along with the speaker. It's only mildly changed the oscillation of the circuit there. So that's how Project 449 works. So Project 450, we're going to take the whistle chip, and now we're going to basically put it across parallel with the C2 capacitor here. So we put it here, And now again we get audio from both the whistle chip and the speaker, but you can hear that the circuit is oscillating slower now because again, the whistle chip adds capacitance from the way it's designed, so that now it's in parallel with this capacitor adding capacitance, and thus is making the circuit oscillate slower. So that's how Project 450 works. Now Project 451, we're instead going to connect the whistle chip in parallel with capacitor C1, so we're going to install it this way now, over top of this capacitor. And again, the whistle chip is producing audio, but now it's chirping a little bit differently, because again, now putting the whistle chip in parallel with that capacitor again also affects the oscillation of the circuit in such a way that it produces different audio. So that's how Project 451 works. Now we're going to have Project 452, which they call the touch control bird sound. So what we're going to do with that is we're going to take our 100,000 ohm resistor R5 here out of the circuit and replace it with the photoresistor. And the photoresistor will then control the resistance in the circuit there, allowing us to change the oscillation of the circuit that way regarding how much light enters our photoresistor here. So I put that into the circuit. And I've already got some light here. See, there's so much light coming in right now that the oscillation is oscillating fast enough to where it's pretty much just a constant tone coming out. And let me take my 6-volt lamp here so I can have a light. Okay. And then as we gradually create a shadow over the photoresistor, you can hear that the tone goes down because we're making the circuit oscillate slower and slower, which of course is lowering the frequency. And then we get it low enough to where the circuit now oscillates to where it can start chirping. And as we lower the resistance there, or I should say increase the resistance as we cover the photoresistor, the circuit oscillates slower and slower. So basically it doesn't oscillate at all when it's completely covered. And as we start letting the light back in, resistance decreases and the circuit begins to oscillate faster and faster. And now let's add another light source onto it with our 6-volt lamp here, which I'll just use off of the battery thing there with our snap wires. And if we bring this closer, the circuit should actually go up in frequency as we decrease the resistance even more. And in fact, when it pretty much goes to almost 0, or just like 1 ohm resistance or so, when it gets very little resistance, the circuit ends up oscillating so fast that it stops functioning. So that is how project number 452 works. So now we're going to move on to project 453, which is the motor sound recording. So here we are with project number 453, the motor sound recording. There it is in the book, and here it is on the board. So we're making use of both 6 volts and 3 volts in this project, and we'll explain what it is. A recording IC and its components are using 6 volts, so you'll have both battery boxes. Of course, in the case of this, we're just using our battery eliminator here. So we've got our typical recording IC circuit set up with our D3 diode for reverse polarity protection, our NPN transistor that's being fed by the recording IC, which then controls our speaker, which is being limited by our 6-volt lamp. And then we have our press switch and slide switch, which both controls the playback of the recording IC and the recording function of the recording IC, and then of course our microphone over here next to the motor, because that's the sound that we're going to be picking up and recording to store in our recording IC. And then of course we have our motor with the fan on it, and that's using a jumper wire which is coming over and connecting over to 3 volts. So if you're using the battery boxes, the jumper wire will come over here to the battery box. So they have it connecting to the negative, but it's actually taking 3 volts off of this battery box here. So take our motor, connect it to 3 volts off of here, and so the motor spins up. Then I'm going to turn on our slide switch and turn our recording IC on. So you got the 1 beep and then the 2 beeps to start the recording and then tell you that it's done. Disconnect power from our fan, and then I'll bring the camera down here. Now we should get the noise of the motor as it was running stored in the recording IC, and we can play it back now. And then of course the recording IC will play one of its 3 built-in songs after the recorded entry ends there. Of course we can play it again. And goes to a different song. So that's how project number 453 works. And now we're going to move on to project 454, which is the motor sound indicator. So here we have project 454, the motor sound indicator. And there it is in the book, and here's on the board. So again, we got 6 volts, but we're again using our battery eliminator circuit. And because of the amount of 3 snaps used in this circuit, I subbed the 3 snap that you would have here with the 6-volt lamp just to act as a 3 snap across that. It's not really doing a whole lot of current through it because it's just driving our green LED. So in this setup we have our S3, which is our relay, and the whole circuit's being turned on and off via our slide switch, but we have our press switch to actuate the relay itself, switching between our green LED, which runs through a 100 ohm resistor, and our 6-volt lamp, which again is acting as a 3 snap, to this point. And then when we actuate our relay, it connects to this point instead, which turns on our red LED, but also turns on our motor, which is in series with our speaker. So as the motor runs, we will hear the EMF that it generates back through the speaker there. So we turn the circuit on, our green LED comes on because we haven't energized the relay, so the current is just going through this loop of the circuit here. But then of course when we actuate it, it will then travel through this loop along with our red LED. So we press the press switch. Our red LED comes on, our motor starts spinning, and we can hear the EMF coming out of our speaker here. And when we release the press switch, the contact opens on our relay and it turns our green LED back on. Close it, turns the motor back on, release it, puts our green LED back on. So that is how project number 454 works. So now we're going to look at project 455, relay and buzzer. So here we are with project 455, the relay and buzzer. There it is in the book, and here it is on the board. And again, we've simplified the circuit a little bit because we're using our battery eliminator providing 6 volts, so we don't have any of the extra connections over here. But the circuit overall is very simple. We just have our relay, and we have one of our contact switch points of the relay connected through our slide switch that turns the whole circuit on and off. And then we have the contact positive side connected along with our relay here. So the relay will be energized when we first turn the slide switch on, and then when it becomes disconnected, it will then close it, which will then reconnect it back here, and then switch it back and forth. So the relay is going to turn on and off very quickly. And while that's happening, we're going to take the on and off, the alternating signal of that, and feed it to our whistle chip to give us an audio output. Now, of course, we'll be hearing all the noise from the electromagnet of the relay as well, but we'll also get that as a signal coming out of our whistle chip. So when we turn the circuit on, the relay actuates very quickly, and we can get an output here from our whistle chip. So that's how Project 455 works. Now Project 456 is the relay and speaker. So what they would do is they would have us replace the whistle chip with the speaker here. Now I'm just going to stick it over top because the whistle chip has got less, the speaker's got less resistance, so it'll just go right through the speaker. So it's going to produce a much louder output of what the relay is doing compared to the whistle chip. So I'm only going to do it a short while because it is pretty loud. So with the speaker, the output is a lot louder compared to our whistle chip, while the relay is turning on and off very quickly. So that's how Project 456 works. Now Project 457 is the relay and lamp. So again, we're just going to take, in this case, our 6-volt lamp, and we're going to put it in place of where the whistle chip would be. In this case, we're just putting it on top because, again, it's a lot less resistance. We turn our circuit on, and our 6-volt lamp lights up. And that's because the relay is turning on and off fast enough that we can't see the 6-volt lamp flickering, but it's enough to actually get the lamp to turn on. Although the lamp is dimmer than it would be if it was on 6 volts because, again, it's reducing the amount of power it can get by turning on and off. So that's how Project 457 works, and now we're going to look at the last set of projects for this video, which is Project 458, the electronic cat. So here we are at project number 458, the electronic cat. There it is in the book, and here it is on the board. So once again, we've got ourselves another oscillating circuit, although it's a little more simplified from our previous one with the bird chirping. And this time we've also got our variable resistor in there instead of a fixed resistor, which allows us to adjust the resistance manually in the circuit there by using the slider, and then of course that will change how the circuit oscillates. So we got our 3-volt setup again with our NPN transistor helping to control the oscillation, along with our capacitors, along with our 100 microfarad that kind of gets the charge and then get the oscillation started. And again, we've got our variable resistor there coupled with our 10,000 ohm resistor to help control the oscillation, which then again goes to our transformer and gets stepped down and outputted to our speaker. But this time we have a press switch instead of a slide switch. So we start with our variable resistor all the way to the left. And I press the press switch, and I'll just bring the camera down to near the speaker for this. So we can try to get some stuff still in frame there. So that's where we have our tone being generated by the oscillation circuit with the variable resistor all the way to the left. Now if we start sliding it to the right, well, let me take the finger off the button first. You hear that the circuit kind of dies out. So it starts up and kind of fades out. And as I change the resistance by sliding our resistor over, you see our tone can change quite a bit to the point where the circuit no longer oscillates, or is oscillating so fast we can't hear it. So that is how project number 458 works. Now, project 459, we're going to connect our whistle chip across our 100 ohm, or I see 100 microfarad capacitor there. So, let's see, points A and B, well, yeah, pretty much across our NPN transistor actually. So we stick it right there, And now we're pretty much getting our audio from our whistle chip. And like before, we can change our resistance. So that's how project number 459 works. Now project 460, we're going to connect the whistle chip across our C2 capacitor. So we'll just take that off there, put it across here. And of course now we get a slightly different sound coming from there, because again of the capacitance that the whistle chip adds in parallel with the C2 capacitor. So that's how project number 460 works. Now project 461, we're going to take our whistle chip and we're going to connect it across C1. So now we're going to put it in parallel with capacitor C1 here. Let's see how that affects the circuit. So again, we get a different tone there, putting it in parallel with that capacitor. That's how project number 461 works. Now project 462 is the buzzer cat. So with that, we're simply going to remove the speaker. So I will just disconnect the power to the speaker. They're doing it that way. And now we're going to take our whistle chip and we're going to connect it across the NPN transistor once again. So this time the whistle chip itself is just doing the audio and not the speaker and whistle chip together. So that's how project 462 works. Now project 463, we're going to connect the whistle chip once again across our C2 capacitor, still leaving our speaker disconnected. So I'll just put that over there. So that's how project number 463 works. Now project 464, we'll take our whistle chip once again. And now we'll put it back in parallel with capacitor C1. Again, still leaving our speaker disconnected. So that's how project number 464 works. Now project 465, it's the lazy cat. So what we're going to do is put our speaker back on, take our whistle chip away, and we're going to replace our 100 microfarad capacitor with the much larger 470 microfarad. So as you figure, if we put a larger capacitor on there, it will take both longer to charge, but also make the circuit oscillate slower because there's more capacitance there. So go ahead and install it, press the press switch. And you can tell that when I release the press switch, the circuit takes longer to die out as that larger capacitor discharges. And then you would basically repeat the same projects again with the whistle chip being connected in various places and then without the speaker again. So just to see how it would sound with the 470 microfarad capacitor. So that pretty much concludes project 465 and this set of Snap Circuit videos.